Okay, we're going to take what we've learned about equivalent systems and apply them to center of gravity in order to get the centroid. Okay, so we're going to take a body, okay, and we're going to break it up into an infinite number of particles that we're going to call dW. They have a weight acting straight down. So basically I have an infinite number of particles acting straight down, so I have a parallel force system. Okay, and the total weight is simply the sum of all of these dWs. So I just sum them up. Now, summing up an infinite number of particles is what an integral is. So the total weight is the integral of dW. Okay, so now that we have the total weight, we then can find the location of the center of gravity. Okay, just like we did with equivalent systems by equating the moment of the total weight W. So I have some location of the total weight W, okay, and I set that equal to the sum of the moments of the weights of the particles. The moment being, okay, the location of the particle times the force downward, right? Well, I have an infinite number of these again, so I have to do an integral. Okay, so I'm just equating basically my resultant load with the sum of all of the moments of the weights. Rearranging each of these for each the x, y, and z direction, I can find the x, y, and z location of the centroid, okay, by just simply taking the integral of the x location of each of the particles times the weight of each particle divided by the integral of the weight of each particle. Okay, so that's how I go ahead and find my center of gravity. Now, to find my centroid, okay, centroid is just defined as the geometric center. Well, the weight of any particle is just mass times gravity. Okay, gravity's constant. Okay, so instead of an infinitesimal weight, I have an infinitesimal mass now. Okay, and then instead of using an infinitesimal mass, I can convert that to an infinitesimal volume, which I can just simply measure, using rulers and things of that nature, by taking rho, which is the density, times the volume, right? And assuming my object is homogeneous, that is, having the same density throughout it, both g and rho come out of the integral, and I'm just left with dV within the integral. So rather than using weights, I can actually use infinitesimal volumes, which is more readily what I can measure on an object in order to find the center of gravity. Okay, so just essentially replacing dW with g rho dV, and g rho is going to be both in the top and bottom, is going to cancel itself out. Essentially what I'm doing is I'm replacing dW with dV, so I can just do this in terms of volume. I can do the exact same thing for the centroid of an area, okay, where I just use dA instead of dV. Okay, so this is how I go about finding the centroid, or the center of gravity, of an object. Okay, so the exact procedure goes like this. So depending on if I have a volume or an area, I'm going to choose a differential element. Okay, if I've got an area, I'm going to use a thin rectangle. Okay, and it can either be a vertical or horizontal rectangle, is just fine. And for a volume, I'll use a thin disc or plate, like I have right here. Okay, once I draw that, I'm going to express basically the dimensions of the element in terms of its coordinates. So this has a width of x, a thickness of dy on my thin rectangle here. On my thin disk, it has a radius equivalent to z and a thickness of dy. Okay. Then I go ahead and I find the centroid of the element. So the centroid of this rectangle is some arbitrary location y. Okay, and x is basically the width of it divided by 2 to find the centroid in terms of my coordinates that I have here. Okay, same thing here. My element is drawn at some arbitrary distance y. Okay, so I just set y tilde equal to y. Then I go and apply those integrals. Okay, I go ahead and apply the equations that I showed on the previous slide, now that I have my differential element all figured out. Okay, so now there's actually an easier way to do this if we've got shapes that I can represent as simple shapes, okay? And we call these composite bodies, which are just a series of connected simple shapes, like a rod, a rectangle, a sphere, things of that nature, where I can easily find the weight and the centroid of each part of the composite body, okay? And once I know the weight and the centroid of each part, I can then just use that equation. But now I have a finite number, right? I'll break this thing into simpler shapes that I easily can find the centroid and the volume of, okay? But rather than doing an integral, then I'm just going to do a sum of, because I'll have a finite number of parts instead of an infinite number here. Okay, so it's the same equation just for a finite number of parts. So the procedure on this is, you start by dividing the body into simple shapes. Okay, break out the circle away from the triangle and the square or whatever it is. Okay, then you determine the size of each part, either the volume or the area, depending on what you're trying to find. If it's a whole, for example, give that a negative area or volume. Okay, so you'll actually subtract that off when you do the summation in that equation. Okay, then you want to find the coordinates of the centroid for each part. So it's a simple shape, so you can easily find the location of the centroid. Just make sure you know those. Once you have the size and the centroid for each part, you can simply apply the equations above to find the centroid of the entire body.